Hi, I'm Mark.
And I'm Callum.
And today we'll be covering some linked list videos.
And here we've got our contents in a linked list.
Yes, so we'll have 3 videos. Our first one will be the prerequisites, where we'll cover a little bit into structs, pointers, and the malloc function. Then we'll cover the absolute basics of what a linked list is and how to implement one. And then we'll jump straight into our first example, which will be some linked list values.
All right. And then in our second video, we'll be looking at some more examples. We'll be looking at prepend, which is adding to the beginning of a list. We'll be looking at append, which is adding to the end of a list. And then sorted insert, which is taking a sorted list, inserting an element so that the result remains sorted. All right. And then lastly, we've got our final video, which will be covering the delete function, and then some extras. And that's the end.
Okay, and just to give you a quick overview as to what a linked list is, in C we have quite a few problems with arrays. A big one that you might have run into is if we would like to add an extra element past the number of elements we specified in an array, we cannot do that. So say, for example, we have an array of length 10, we cannot add an 11th element. So a linked list is a workaround. I don't say solution because there's no perfect solution. There'll be advantages and disadvantages of quite a few workarounds. But in this video, we will just cover linked lists. So now we'll be doing our first prerequisite video on structs. So if we recall, we can think of a variable as like a box in which we can store a number or a value, whatever we would like. So in this case, we'll store the integer 3. So over here, we have a struct, and it's very similar to a variable, except it's more like a cupboard. It has lots of shelves and drawers, and we can store lots of different variables inside it. And just like a cupboard, you have shoes, shorts, and shirts. They're all different types of clothing. Here we can have different types of data, so different data types. So here we have an integer 3. We have a double 1.618. Here we have a char b, and here we have an address. So this would be a pointer. So this is our definition for the struct. This is what the code would look like to create a box which is actually empty, doesn't have these, but it would specify what we want and expect in these positions. So now I'm going to quickly fast forward, and I'm just going to show you what it would be like to declare an integer and then set a value into an integer, and show you how you do the same thing with the struct, and you can see the differences. Okay, so I've written up the code, and we can see over here, we've got step 1, the declaration. So how we declare an int is we say, okay, my int is of type integer. And step 2, we're assigning our value, assignment, and we'll say my int equals 3. And that's how we set the value of an integer. Here, it's similar. It's just a little longer because we have to set each of these fields individually. So step 1, the declaration. So just like int is the type over here, struct, test struct is the type, as you can see defined here. And my struct is the name, just like my int is the name over here. And then declaration, we're going to assign each of these individually. So straight away we'll go my struct dot my int equals 3. So if this dot notation isn't familiar, maybe just go check the lecture notes. It has been covered in lectures. So here we can set all of the values. So similarly, my double, my char, my pointer. Here I put on the next line because it didn't quite fit, and that should assign all of these fields. Now for the second prerequisite video, we'll be covering pointers. If we recall, an integer stores a whole number value. A double stores a number with a decimal point. And, well, a pointer, it just stores the address of something. So just keep that in mind. And I'm also going to explain this quick cheat sheet over here. So the ampersand in my head is address of, and the asterisk or star is the value of. Now, I'll explain why the value of is a bit colloquial once I get down to this bottom line in just a moment. So first off, we're just going to create an integer of type, we're going to create a variable myInt of type integer, and then we're going to set it immediately equal to 42. Now we're going to create another variable of type intPointer called myIntPointer, and we're going to set it equal to the address of myInt. So now myIntPointer stores the address of this int up here. So now if I want to change myInt without actually explicitly resetting the value there, if I want to change it by using the pointer to it, I would say the value of the thing myIntPointer points to is now equal to 100. So that's where the value of comes in with the star. It's important to note that this star does not mean value of, that is a type. Int star means, or asterisk, means int pointer. this star is different to this star. This is the dereferencing star to get the value of. So similarly, if we have a look at this struct over here, we've got a struct definition over here. So these two lines are very similar. Just like we're making an int here, we're going to make a struct student called Bob. And just like we're setting the value here, we're going to set the value of Bob with these three lines, setting each of the fields in the struct individually. So just like we're creating an int pointer over here, we're going to create a struct student pointer, something that points to a struct student like this. And that's going to be called my_str pointer. And that equals the address of Bob, just like we made this the address of my int. So now if we want to change one of the fields in Bob, or multiple of the fields in the Bob struct, what we will do is, just like over here where we are dereferencing using this star, we'll say the value stored, the value that my_str pointer points to, well, the wham component of that, we're now resetting to 72.8. Now, this is a bit long and a bit hard to comprehend. So there's a bit of syntactical sugar, a little shortcut, where you can take these parentheses and this asterisk as well as that dot and just put an arrow instead between the elements. Now, we use the my_str dot without the asterisk if we're referring to a struct, like just a regular struct, and we only use the arrow if we're referring to a pointer to a struct. So that's really important to remember. So now we'll be covering the third prerequisite, the malloc function. So over here, there's kind of a long expression, and this is the syntax for malloc. Essentially, if we want to designate an area of memory that looks something like this, like a struct, it might look like this, and we want to get a pointer to an area of memory which will store a struct. I guess we can denote that by this. So we want this pointer to a struct. What we will do is this rather long line over here. We'll say, okay, we want to make a new pointer over here. It's of type struct student pointer, and we want to store this pointer in the variable new student. So that would be this. This would be new student. Now, in order to give it this pointer, we have to use two very special bits of syntax here. So malloc is a way of assigning us an area of memory. So this will give us this chunk of memory. It's defined in an area called the heap. That's not so important to remember right now. It's just good to know that it exists. And how do we specify how much memory that we want to be designated for this struct? Well, we use this inner thing here. I tried to make my brackets different sizes. So we say size of struct student. So it'll say, somewhere we'll have a definition for struct student, and it'll count up all the different fields we have in a struct student. So an integer will take up 4 bytes, and a char will take up 1 byte. And this will give us the size of how big all these different components need to be. It'll make a chunk this big. Then malloc itself, it takes a number. So this over here will turn into a number, and it will return to us, malloc will return to us a pointer, which will store, well, an address to this area of memory, which will store in this pointer. And that would be this. So that's our syntax. So the reason why we use malloc is so that our memory stays after we leave a function, because as we remember, when we return from a function, everything that was defined in that function gets lost. So actually, we won't be able to access new student anymore, but this area of memory will persist. So if we want to still be able to access this area of new memory, we need a way of actually returning this pointer over here. It's important that we don't lose our pointers, or because that means that it'll get lost in a huge, the huge, vast ocean of memory. There's so many memory addresses, and it's like dropping a needle in a haystack. You can't reasonably expect to find it again after you lose your pointer. So you always have to make sure that you have something which will point to your struct. Okay, now you can use that pointer in order to access the elements of the struct, but you can also use it, and you should definitely use it, to free your struct once you're finished. This syntax over here is a way of passing the pointer. Remember, new student is a pointer. You pass a pointer to this function called free, and what it will do is it will make this memory writable again. So it'll mean that you're finished using it, and the computer can reassign it for other tasks and processes to use. It's important that you do this to avoid having memory leaks in your programs. Okay, great. So now we're going to do the actual main bit of the video, where we're going to evolve a struct into a linked list. So first, you'll notice over here a struct definition. So in Callum's code, he's going to do it slightly different. He's going to have this pointer, this second field, at the top, and he's going to have the data at the bottom. We're doing it like this so you can see it's actually interchangeable. It doesn't matter which order your fields in the struct are. So I'm doing it this way so it makes more sense with my diagrams. So now going straight into it, we're going to evolve our student struct, right? We no longer need ZID and that sort of stuff. Instead of calling it a student, we're going to call it a node. And in it, we're going to store two things. We're going to store data and a pointer. And you'll see why in just a moment. So imagine we just had a regular variable over here. Let's say we had over here 1, 3, 3, and 7. So this would be as if we had 4 regular variables. These are not structs. But imagine if we did make them structs and we didn't define them like a regular variable, but we actually malloced them like we looked at in the previous segment of the video. So this is the syntax in case you forget. And we're going to malloc 4 nodes. So using 4 of these statements. I didn't write them all down, but the only thing that we would change is instead of node 1, we do node 1, node 2, node 3, node 4, and node 4. So over here, going back to this, what we would actually end up with is not 4 variables, or what it looks like variables, but we'd end up with 4 pointers to these structs, right? It would look something like this. Now notice that this is not the same as this struct definition. I've only included the data field for now. It's as if we haven't coded in this last line over here. That's what we're going to do now. So this isn't very useful. If we wanted to store something like this, we might as well just define 4 integers, right? So instead, we're going to do a few things. We are going to add a new field. So this is where we're going to add this struct node star next. Notice here I've circled the data types so we can remember that this star is part of the data type and it's not a dereferencing star. So next what we'll look at is how to evolve this into a linked list. So what we are going to do is we're going to use this second field, this pointer called next, which points to another struct node. So all of these are struct nodes. So looking at the next diagram, what we're going to do is we're going to get, I just moved this pointer up here so that the diagram makes a little bit more sense. And what we're going to do is we're going to get this node over here to point to the second node, the second node's pointer field to point to the third node, and the third node's pointer field to point to the fourth node. So I'm just going to fill in my values over here, 1, 3, 3, and 7. Now what we do with the last node is we make it point to null. So null is a place where we get things to point if we don't want them to point to anything. It's like initializing a variable. We initialize our pointers to null. And this is a way that we can tell we're at the end of the list. Okay, so how do we actually firstly insert our values into not just a struct node, but here we have actually a pointer to a struct node. So we use this first line of syntax. We're saying not the data type. A lot of people, when they're doing this, they say node arrow. Here we use node 1, which is what we called our struct. We're going to say node 1 arrow value equals 1. This will put a 1 in our field. Similarly, we can put 3, 3, and 7. In order to change the pointer element of our struct, what we're going to use is this arrow over here, but with next. So we're going to say node 1 arrow next, because this field over here is called next. And so my question, have a quick think about it, is what are we going to put here? Are we going to put ampersand node 2? So we want the first one to point to the address of the second one? Or are we just going to write node 2? So with some brief thought, we remember that these are pointers in themselves, which means that struct 2 is in itself an address. It stores an address, which means over here we can just, before I said struct 2, I mean node 2. So we can just get it, we can just have it so that node 1 next points to node 2. And that is enough. We do not need our ampersand here. And so that's assigning things to our struct. Now over here, I wrote this so you can see the actual syntax for having the last element point to null is actually the capital letters NULL. So we'd say node underscore 4 next will equal null. Just over here we'd write null instead of node 2, and over here we'd write node 3. And that just about sums it up for linked lists, the evolution of a struct into a linked list. And now over here, this is a linked list, and we have our first linked list. So now we'll speak about using current to move through your list. So in the last segment, we spoke about how we would malloc a series of nodes. In this case, we had 4 nodes, and we were left with pointers over here, these 4. I just moved the one up the top, so it would move. I just moved it over here, so the diagram would make a bit more sense. On the very last diagram in the last segment, I actually forgot to leave these in. So I wanted to quickly speak about that. So because we malloced these structs will stay with us until we free them, and we have not freed them yet. But these pointers, these will also stay until we return from our function. Now, we don't have to worry about these pointers, well, these 3 at least. We do, however, have to worry about this top one, because we need at least something to point to the rest of our list so we don't lose it. We need at least a pointer to point to a specific area of memory so that we can access everything below it. So just by having this one here, we can access the first one. And by having this one here, we can access the second, and so on, all the way till we get to our last one, which points to null, which means that well, it doesn't point to null, it contains null, but that's a formality. Cool, so yes, we don't have to worry about these anymore, so in the next one, I've rubbed it off. Assuming we returned from a function, and we returned just this first pointer. Another key point is something that makes linked lists very useful is the fact that the reason why we don't have to store all these, the fact that we don't have to store all these makes it very useful parsing linked lists into and out of functions, because we only have to pass in or pass out this one pointer. Okay, so moving on, we're going to speak about iterating through a list, or moving through a list. So, we're now going to create another pointer. Now, we've made a lot of pointers which point to new areas of memory using malloc. Now we're going to make a new pointer which doesn't actually have its own chunk of memory, but rather points to another area of memory which is already defined. So it's as if we have something like this, where we have 2 pointers to an area of memory. However, this one we got from malloc, which is slightly different. So, using this syntax, we're going to create something called current. I'm just going to denote it by a C. And then using this next line, we are going to initialize it to point to head. Now, I called head the first pointer. As I said, we have to remember one pointer. In the previous video, I called it node 1, but it makes a bit more intuitive sense to call it something sensical. So here, I'm going to call it head. So current next. So the thing that current points to will be over here, like this. Cool? Now, what we're going to do is we're going to use this third line over here, current equals current next, in order to move current through the list. So say, for example, I wanted to change this 3 to the value 9. What I would do is I would execute these 2 statements to create current and make it point to the first node. Then I would execute this third statement in order to get current to move down 1. So it would look something, a little bit smudged, something like this. Right? Now I can execute this 4th line. Now I put this in a different color because this is interchangeable. I could set it to whatever value I want. So that would take this 3 value and it would change it to 9, like this. So we can actually access elements of current as if we had the actual node, but because we have a pointer to it, which is exactly as if we had this pointer. Well, we just pretend like with this arrow instead of this arrow, so we can still access the same elements. Similarly, we could use current next equals, and we could assign it to another node if we wanted to. We could make this one point to the bottom if we wanted to get rid of this, but we'll deal with that in another video. Okay, so now let's say I want to know when to stop iterating through a list. Well, I can keep executing the statement, and you'll often see it in a loop. You'll see that in the code very soon. And I can just use current equals current next as my at the end of a while loop, you normally have I++ or some way of incrementing a counter. You can think of this kind of like a counter. It's an exit condition. You often have while current is not equal to null, or while current next is not equal to null, depending on the problem. You want to do your code, and at the end, current equals current next. So you could like do a whole bunch of run-throughs and then iterations of this loop, and eventually you'll end current here, and in that way you can do an operation with the last node. But we'll see that in the next example. So using what we just learned in the last segment, we're going to use current to iterate through a list, and we're going to use it in our first example program, our first example function. It's going to be a sum function, and in our code, which you'll see in just a moment, we're going to call it sum node values. Okay, so the first thing we have to remember is, well, first of all, we should know what the function does. So it'll take all these values stored in our linked list, so 1, 3, 3, and 7, and it will sum them and return the result. In this case, it will return 14. So using these two first statements, like we did in the last video, we'll declare a current pointer and have it point to our first node. Then we're going to declare our own sum variable, and it's going to be just a regular integer, and we're going to initialize it to 0. Then in our loop, we're going to use these two statements in order to collect this value stored in the node which current is pointing to, and we're going to take that value and we're going to store it in sum. We're going to take sum and we're going to add that extra value. So sum should eventually accumulate all the values by the time it reaches the last node. So we will have a loop, and our condition would be something along the lines of while current is not equal to null, we want to take this value, we want to accumulate it in sum, we want to add it to our sum variable, and then we want to move current down using this line over here, current equals current next. We want to keep doing that all the way till we get to our last node, and eventually current at the end of our loop will point to null, and that is our condition to stop our loop. Now you'll see that just a moment when Callum does his coding. So just to conclude, linked lists are not an extremely new concept. They're just taking things you already know, like structs, pointers, and functions like malloc, and applying them in a way that they're really, really useful to us in the form of a linked list. Now, over here, I've got another linked list, this time with 3 nodes, and they've got some negatives and 0 values, just to mix it up a little bit. And we're going to use this statement over here using this function, get value at index. Now, this is a homework problem that I'm going to leave for you guys to do if you choose to. And given a list L and a number 2, it'll get you the value stored at the second position. So this should return -4, which you'll now store in value, and then you can print that out or use it wherever you'd like. So I'm going to leave you to think what your function definition would look like and everything else. You can use this struct definition over here. Okay, thank you for watching. In the next video, we'll cover some harder examples, and that's it.